Welcome to this video on the Introduction to ANOVA Part 3, the F distribution. Let's begin. After watching this video, you should be able to state which test statistic is used to conduct an ANOVA test, describe the F distribution, provide a basic formula for the F statistic. ANOVA stands for Analysis of Variance. This statistical method serves as a comparison of quantitative data among several, meaning more than two groups. So we could use it to compare 3 or 4 or 5 or more groups. ANOVA, or Analysis of Variance, asks the question, could these different samples have come from the same population, or is there enough difference among them to suggest that at least one of the samples was taken from a different population? ANOVA is a hypothesis test with the following hypotheses. The null hypothesis is that all of the means are the same. Alternatively, we suggest that at least one mean is different. Recall, as we discussed in the previous video, this test does not tell us which mean or means differ from the others, and it does not tell us how they differ. As with other hypothesis tests, to conduct an ANOVA hypothesis test, we must compute a test statistic and compare it to a critical value. But what is the test statistic we use for ANOVA? In previous hypothesis tests, we have used the Z distribution or the T distribution. Notice that both distributions are symmetric. Recall, the shape of the student T distribution changes as the degrees of freedom change. The F distribution is a right-skewed distribution that is most commonly used in analysis of variance tests. When using the F distribution to perform a one-way ANOVA, we always conduct a right-tailed test. The shape of the F distribution will vary depending on the number of groups you are comparing, M, and the size of the samples, N. The F distribution has not one, but 2 degrees of freedom. The numerator degrees of freedom, or DF1, is calculated as the number of groups M minus 1, or M minus 1. The denominator degrees of freedom, or DF2, is calculated as the total sample size, N, minus the number of groups, M. So DF2 is equal to N minus M. In general, we call the variability between different samples the between groups variability, and the variability within each sample the within group variability. The F statistic compares the variance among the groups with the variance within each group. So the F statistic is the ratio between these two variances. F equals the between groups variance divided by the within groups variance. An F statistic close to 1 indicates that the variance within each group is about the same as the variance between the groups. This suggests that the samples could have been taken from the same population. F statistics close to 1 lead us to retain the null, suggesting there is no difference among the means. The farther above 1 the F statistic is, the more likely we are to reject the null in favor of the alternative hypothesis that at least one mean is different. So let's use a practical example. A roller skating rink hosts children's birthday parties. 3 randomly selected samples of children are chosen, and the ages of the children are recorded. In this first distribution, is it likely that each of the 3 samples came from the same children's birthday party or from different parties? Let's use range as a shortcut for measuring variation. So I want to clarify here that what I'm about to show you, or what I'm about to do, is not at all the proper or correct method for calculating the F statistic. Instead, it's more of a visualization to help you understand, by looking at the distribution, why it makes sense that an F statistic close to 1 leads us to retain the null. So let's start with this value here, right? So remember, the F statistic is the between groups variance. So if I use range as a shortcut for variance, the range of all of the data sets clumped together, right? This is the between groups variance, goes from 4 years of age to 13 years of age. So 13 minus 4 is 9. So the between groups variance, again, not really, but let's just pretend that we can use range in place of variance. The between groups range is 9 years. So I'm going to take each of these groups separately. And again, you can see that this is not a real F statistic because in reality, you would only have a single number, not 3 different numbers. So let's look at the blue group. So the range of ages in the blue group is just 2 years, right? So if we have the between groups variance, that was 9, right? The between groups range was 9 divided by the range of the blue group, it's 2. So 9 divided by 2 is 4.5. Right? So the variances are very different from each other. Again, suggesting that probably, right, the data came from different populations, leading us to reject the null. We can do the same thing with the pink group. So the pink group, again, the range is 2 years. So again, the between groups variance is still 9, right? The range of the whole data divided by the range of just the pink group. So again, we have 9 over 2 of 4.5. So very different ranges, again, suggesting or hinting to us that maybe these data points came from different populations. And last but not least, if we look at the green group, we can see that we have a range of 3 years. So we have 9 divided by 3, which is 3. Okay. Again, I cannot emphasize enough, this is not a correct or appropriate calculation for the F statistic. It is very merely just a visualization to help you see that if the ratio is close to 1, then you would suggest that, oh, probably they came from the same population. When it's very far from 1, then it suggests that the data points came from different populations. So in conclusion, right, all of these values are larger than 1. So that would lead us to reject the null hypothesis. Remember, the null hypothesis for ANOVA is that all of the means are the same, or that even though we got different samples, we think that we're actually sampling from the exact same population. So if we look at all 3 samples, it seems likely, right? Let's just think about a children's roller skating party, right? So who is this party for, the blue group? Well, it's probably for 5-year-olds, right? So they have 4, 5, and 6-year-olds. So it's probably one party right here. There's probably a second party for 8-year-olds here, right? So they have 7, 8, and 9-year-olds, right? And then there's probably a third party right here for, I don't know, 11 or 12-year-olds. So they have kids here that are between 10 and 13 years old. So it makes sense that we are sampling here different populations rather than sampling a single party. So let's look at the exact same scenario where we are sampling, where we have 3 samples from a roller skating rink. Okay, but now hopefully you can see just by looking at this cute little dot plot here, right, that our data is very differently distributed. Let me just go back really quickly, right? Here, all the blue dots were clumped together, right? All the pink dots were clumped together, all the green dots were clumped together, right? And the clumps didn't even overlap. Do you see that? Right? Now, here we have a lot of crossover. We have a lot of overlap. So let's do the same thing again. We are just doing a quick and dirty visualization. We're using range to represent variation. It is not the same as variance. We're just trying to visualize what we mean or what we're doing when we calculate the F statistic. Okay, so the range from the smallest data point to the largest data point for all the groups is 0 to 15, so we have 15 years. So our between groups range, if you will, right, what we're using to approximate the between groups variance is 15. Okay, so let's look at our we start with our pink group. Here's our pink group. Okay, so our pink group goes all the way from 3 years old to 15, so we have a range of 12 years. So our ratio, 15 to 12, is about 1.25. Okay, then we do the blue group, blue to black, and the ratio is 15 to 14, or about 1.1. Okay, then we have our green group, so that is 15 to 9, or 1.6. So what does this mean? Are the F statistics, again, that we just kind of cobbled together, not really using at all the correct formula, but just looking at and comparing the ranges, the between groups range and the within groups range, does it suggest that these 3 samples are coming from different populations or the same population? Well, I don't know about you, but I could buy the argument that all 3 samples are coming from the same roller skating party, right? the ranges are quite similar. So I could imagine that maybe somebody was having like a family party, right? So not just a birthday party for like a 5-year-old or a 10-year-old, but maybe a family party where you have infants, because you have kids who are way too young to roller skate over here, right? But you can't leave them at home. So maybe it was a family party or a family reunion, and you have kids all the way up to 15 years old. So again, because there's so much overlap and because the range or the variation within each group is not very different from the range among the groups, right? Because they are close in value, then we don't have sufficient evidence to suggest that at least one of these samples is different. So we have to assume that that they came from the same population, or we don't have enough evidence to support the argument that at least one of them is different. So now that you've watched this video, you should be able to state which test statistic is used to conduct an ANOVA test. Of course, as you all know, that's the F distribution. You should be able to describe the F distribution. You might recall it is a right skewed distribution, unlike the Z and the T distributions, which are symmetrical. And unlike the T distribution, which only has 1 degree of freedom, this distribution has 2 degrees of freedom. And remember that the shape of the distribution, just like in the T distribution, is going to become less strongly skewed as the degrees of freedom increase. And remember, the way the F statistic is calculated is to find the ratio of the between groups variance to the within groups variance.